Hi guys, this presentation is dedicated to finding the impact of metal oxides on air pollution. My name is Shashank Shrikant. I am an online student. So let's dive right in. So the purpose, before we go into the analysis, I just wanted to tell you guys the overarching purpose of this project. What is the solution, or what is the problem actually we're trying to solve? And the problem in broad terms is climate change. This is a quote from the Intergovernmental Panel on Climate Change, and the panel said that scientific evidence for warming of the climate system is unequivocal. It is not up to debate. It is an agreed upon fact that it is a huge problem. One of the biggest problems actually we face today. So how can we combat it to the best of our abilities? So this drove me to look towards air pollution. According to the Institute for Advanced Sustainability Studies, IASS, air pollution and climate change are actually very closely related. Air pollutants affect the amount of sunlight absorbed and reflected by the atmosphere, and increased air pollution leads to warmer temperatures. Sorry. So, which gaseous elements then contribute to the rise in temperature? And that essentially is the big concept of this presentation. If we know which gaseous elements contribute most, which pollutants contribute most to the increase in temperature, we can take steps towards reducing their emission. Individual steps, changing our habits, tweaking it a little bit to make sure that we don't emit high amounts of those pollutants into the air. So, the dataset logistics, I will be talking about which dataset I used, the technologies I used, and what methodology it was. So dataset analyzed. The air quality dataset was obtained from the UCI machine learning dataset database. The dataset has several different metal oxides in the air over a period of 1 year in a bustling and heavily polluted and populated city in Italy. The concentration of metal oxides in the air will be our independent variables, and the temperature will be the continuous dependent variable. And these are the 5 metal oxides we're going to be looking at: carbon monoxide, non-methanic hydrocarbons, benzene, nitrogen dioxide, and other nitrogen oxides. NOx is just a generic way of representing in chemistry generic nitrogen oxides. So the technologies used in this presentation was Excel, K9, and Python. It was a mix of all three. I will be going further into how they were used specifically. So a simple Python script was used for very basic pre-processing, reading in the CSV file, renaming and deleting columns, and downloading it on to my laptop as a new CSV file. And there were some columns that had to be deleted, for example date, time, the humidity in the air, the absolute humidity, and the hourly average sensor responses. These concentrations in the air were recorded by sensors, and the hourly average sensor responses is how many times they pinged with calculations per hour. That really does not contribute to an increase in temperature, and neither does the date or time or such, so these columns were deleted. Excel now was used for the majority of the data cleaning. A lot of data in this dataset was actually strings. Even though they were integers, they were in double quotes, so that had to be dealt with. The dataset also used commas as decimal points, so 2,6 instead of 2.6. Some places in Europe use a comma instead of a decimal point, so I had to get across that barrier. And missing values, so I worked on missing values by replacing it with the average of the column. So for instance, if the missing value is in the carbon monoxide column, it was now replaced with the mean of the carbon monoxide column. And K9 was used for visualization, so scatter plots, histograms, correlation tables, and such. And the bulk of the data analysis actually came from a Python script. So this included splitting the dataset into a training and testing set, 70% training, 30% testing, and then I used linear regression. So I added one variable at a time, so one oxide to the equation at a time, and every time I added a variable, I monitored the RMSE of the testing set. If the RMSE decreased, it meant the variable added to the performance of the model. And that is the order in which they were added. It was CO, NMHC, C6, H6, NOx, and then NO2. So summary and visualizations, what did I actually get from employing all these technologies? So this is a statistical summary. On the left you can see the columns, the metal oxides, and the minimum, the maximum, the mean, standard deviation, variance, skewness, kurtosis, and such. And on the right are the histograms, and it's very interesting to see because almost all of these histograms are skewed right. That was a very interesting observation. Not sure why that exactly happens, but that is the case. And for the second one, NMHC, you can see that there is a heavy spike in the 7. Actually, we had immense levels of missing values for NMHC. So since it was replaced with the mean, the mean was the highest occurring value for NMHC, which is why we see that spike. And the histogram of temperature is indeed our dependent variable, so I wanted to make a histogram of it to see its distribution. It's a unimodal distribution, and it does have an outline of a bell curve. It is shaky at a few places, but it is representative of a bell curve. And now these are our scatter plots. There is quite a bit to unpack here actually. There is no strong linearity between temperature and the independent variables, but we can see slight linearity in the case, for example, of benzene, which is C6H6, which is right over here in the down middle. That does have a slight linear relationship, and so does NMHC, kind of, with the scattered plots over here, but the straight line doesn't exactly contribute to the linear relationship. So that is what we can glean from the scatter plots. And then we look at correlation, mainly multicollinearity. Research suggests that 0.5 or above indicates multicollinearity, where one independent variable affects another independent variable. So since we do not have any values over 0.95 except the diagonal, which saw once, because correlation with the same independent variable is always 1, we do not have multicollinearity. The strongest positive collinearity in regards to temperature is between temperature and benzene, so we can assume that benzene has a significant impact on the rise of temperature, and the same can be said for CO and temperature, because that is the second largest positive correlation. And we can support these two conclusions through linear regression. So we're going to go into next. So as I said before, a training and testing set was 70% and 30% respectively, and the addition of each variable to the model reduces the RMSE. So here I have a table. So to the equation I first added CO, and the RMSE was 8.743, and then I added NMHC to the model and it decreased, and then I added benzene and it decreased again, and then I added NOx and we see a significant decrease in RMSE, and then I added NO2 and we see a slight decrease in RMSE. So as I said before, each variable does reduce the RMSE. So this is our final equation. The temperature equals 18.557 plus 1.152 times CO minus 0.02 NMHC plus 0.667 benzene minus 0.031 NOx and minus 0.012 NO2. So we can see that carbon monoxide and benzene actually contribute to the increase in temperature. So for every milligram per meter cubed increase in CO, the temperature increases by 1.152 degrees Celsius. And for every milligram of meter cube increase in benzene, the temperature increases by 0.667 degrees Celsius. So we can therefore change our actions, tweak it a little bit to reduce the emission of CO and benzene. I do not have any ideas in this presentation, but the internet is flooded with them, so I would recommend you guys check that out. So conclusion, what could have been done different? Quite a few actually. Handling the missing value problem more efficiently. I replaced it with the mean. I could have instead implemented a multiple imputation algorithm. This would have also not introduced any bias into the analyses and would have been a little bit easier. And also we looked at the data, we looked at the scatter plots, there wasn't a strong linear regression, so maybe a quadratic regression could have been the way to go. So if I had more time, I would have definitely gone into that and seen if that would have made a better model. And that is my presentation, and this is just works cited. Thank you guys. Thank you.